Deep beneath our feet, hidden by miles of rock and molten magma, lie secrets of unimaginable scale. These are the stories of Earth's formation, of continents colliding and oceans opening. Here, in the heart of our planet, colossal structures hold sway over the very ground we walk on. These are the large low-shear velocity provinces, or LLSVPs, enigmatic giants that play a pivotal role in the grand drama of plate tectonics. We live on a planet that is constantly shifting, its surface a jigsaw puzzle of moving plates. Mountains rise and crumble, oceans expand and shrink, all thanks to the forces deep within the Earth. But what drives these plates? What lies beneath the surface orchestrating these monumental changes? The answers, it turns out, are intimately intertwined with the LLSVPs. Imagine structures so vast they dwarf entire continents. These are the LSVPs, mysterious zones located deep within the Earth's mantle. Their existence, hinted at for decades, is now being revealed through sophisticated imaging techniques. These techniques, like seismic tomography, allow us to peer into the Earth's interior, much like an ultrasound reveals the secrets within a human body. These LLSVPs, we are beginning to understand, are not just passive bystanders in our planet's evolution. They are active agents of change, influencing the movement of continents, the birth of volcanoes, and even the course of life itself. Their story is a profound reminder of the immense power and mystery hidden within our planet. Imagine trying to understand the workings of a clock without ever being able to open it. You can hear it ticking, you can see the hands moving, but the intricate mechanisms inside remain a mystery. That's the challenge faced by Earth scientists studying the planet's interior. They have to piece together clues from the surface to understand what's happening deep below. We can't simply dig down to the core. The heat and pressure are far too intense. The deepest humans have ever drilled is just over 12 kilometers, a mere scratch on the surface. Instead, we rely on indirect methods, much like a doctor uses X-rays to see inside the human body. These methods allow us to peer into the Earth without physically reaching those depths. One of our most powerful tools is seismic tomography. This technique is akin to taking a CAT scan of the Earth, using seismic waves to create detailed images. This technique uses waves generated by earthquakes to create images of Earth's interior. When an earthquake occurs, it sends out waves that travel through the Earth, and these waves can be detected by seismometers around the world. Just as sound travels at different speeds through different materials, seismic waves speed up or slow down, depending on the density and composition of the rocks they pass through. This variation in speed helps scientists infer the properties of the Earth's interior. By analyzing these subtle changes in wave speed, scientists can create three-dimensional maps of the Earth's mantle, the layer between the crust and the core. These maps are crucial for understanding the structure and behavior of our planet. It was through these maps that the LLSVPs were first revealed. These large, low-shear velocity provinces are among the most enigmatic features of the Earth's interior. These massive structures, located near the bottom of the mantle, are defined by their unusually slow seismic wave speeds. This indicates that they are composed of materials that are different from the surrounding mantle. There are two main LLSVPs. These colossal structures are found in two distinct locations on opposite sides of the planet. One sits beneath the African continent, stretching across a vast area and influencing geological activity in the region, while the other resides under the Pacific Ocean, affecting the dynamics of the oceanic crust and volcanic activity. These are not small features by any means. They are some of the largest structures within the Earth, dwarfing even the tallest mountains on the surface. The African LLSVP, for example, is estimated to be around 1,000 kilometers high and thousands of kilometers wide. This makes it one of the most significant geological features on our planet. To put that in perspective, Mount Everest, the tallest mountain on Earth, is a mere 8.8 kilometers high. The scale of these LLSVPs is truly staggering. But what exactly are these LLSVPs made of? Their composition remains one of the biggest mysteries in geology. Their slow, seismic wave speeds tell us they are denser than the surrounding mantle, suggesting they may be composed of different materials. This density difference is a key clue in understanding their nature. Some scientists believe they could be remnants of an ancient magma ocean that existed early in Earth's history. This theory suggests that these regions have preserved materials from the planet's formative years. Others speculate they are regions where subducted tectonic plates have accumulated over billions of years. These plates, having sunk into the mantle, may have formed these dense, slow-wave regions. The Earth's surface is a dynamic and ever-changing landscape, constantly in motion and transformation. What we perceive as solid ground is, in reality, a collection of massive tectonic plates, constantly shifting and grinding against each other, driven by forces deep within the Earth. This movement, driven by the heat escaping from Earth's core, is responsible for the creation of mountains, the opening and closing of oceans, and the occurrence of earthquakes and volcanoes. These processes shape the very surface of our planet, creating the diverse landscapes we see today. This continuous dance of the continents is known as the Wilson cycle, a fundamental concept in the field of geology. Named after the Canadian geophysicist J. Tuzo Wilson, the Wilson cycle describes the cyclical process of continental rifting, seafloor spreading, subduction, and continental collision. Wilson's groundbreaking work has provided us with a deeper understanding of the dynamic nature of our planet. It's a story that has played out over billions of years, shaping and reshaping the face of our planet. The Wilson cycle is a testament to the ever-changing nature of Earth's surface. The cycle begins with continental rifting, where a continent, under the influence of rising heat from the mantle, begins to thin and stretch. This initial stage sets the stage for the dramatic changes that follow. As the stretching continues, a rift valley forms, much like the East African rift we see today. This rift valley is a clear indication of the powerful forces at work beneath the Earth's surface. Eventually, the continent breaks apart, and a new ocean basin is born. This marks the beginning of a new phase in the Wilson cycle. As the ocean basin widens, new crust is generated at mid-ocean ridges through a process called seafloor spreading. This process continuously adds new material to the ocean floor. This new crust pushes the continents further apart, carrying with it a record of Earth's magnetic field, frozen in time. These magnetic records provide valuable insights into the history of our planet. Over millions of years, the ocean basin reaches its maximum size, a vast expanse of water separating the continents. Then the cycle begins to reverse, initiating a new series of geological events. At the edges of the ocean basin, the denser oceanic crust begins to sink beneath the lighter continental crust in a process called subduction. This process is a key driver of the Wilson cycle. This subduction zone is marked by deep ocean trenches and chains of volcanoes. These features are visible reminders of the powerful forces at work beneath the Earth's surface. As the oceanic plate sinks deeper into the mantle, it melts, and the molten rock rises to the surface, fueling volcanic eruptions. These eruptions are a dramatic display of the Earth's internal energy. Finally, as the ocean basin closes, the continents on either side collide, crumpling and uplifting the land to form towering mountain ranges. This collision is a powerful force that shapes the Earth's surface. The Himalayas, for example, are the result of the ongoing collision between the Indian and Eurasian plates. These majestic mountains are a testament to the power of tectonic forces. And so the cycle is complete, only to begin anew millions of years later. The Wilson cycle is a continuous process, a testament to the dynamic and ever-changing nature of our planet. The Earth's mantle, far from being a homogeneous layer of rock, is a complex and dynamic system, teeming with activity and variations in temperature and composition. Within this churning mass of molten and semi-molten material, heat is constantly transferred from the Earth's core to the surface, driving the very process of plate tectonics, which in turn shapes the surface of our planet. And it is here, in the lower mantle, that the LLSVPs, or large low shear velocity provinces, exert their influence on the Wilson cycle, shaping the destiny of continents over geological timescales. As we've seen, continental rifting is the first stage of the Wilson cycle, the process by which continents break apart, drift, and eventually collide to form new supercontinents. But what triggers this rifting? What forces are powerful enough to tear continents asunder? While the exact mechanisms are still debated among scientists, there is growing evidence that LLSVPs play a significant role in this monumental process. These massive structures, with their distinct chemical composition and hotter-than-average temperatures, are thought to generate plumes of hot, buoyant rock that rise through the mantle, creating hotspots and volcanic activity. When these plumes reach the base of the lithosphere, the Earth's rigid outer layer, they can cause it to bulge upward, weaken, and eventually rupture, leading to the formation of rift valleys and new tectonic boundaries. This process, known as plume-induced rifting, is thought to be responsible for the breakup of supercontinents and the formation of new ocean basins, fundamentally altering the geography of our planet. But the influence of LLSVPs goes beyond simply initiating rifting. They also play a crucial role in the ongoing cycle of crust creation and destruction. As new oceanic crust is generated at mid-ocean ridges and spreads outward, it eventually encounters a subduction zone, where it sinks back into the mantle, recycling the Earth's crust. Recent research suggests that LLSVPs can act as barriers to this subduction process, influencing the dynamics of plate tectonics in ways we are only beginning to understand. When a subducting plate encounters an LLSVP, its descent can be slowed or even stalled, affecting the overall movement of tectonic plates and the geological activity associated with them. This interaction between the subducting slab and the LLSVP can have profound consequences, potentially influencing the location and intensity of volcanic activity, the formation of mountain ranges, and even the motion of entire tectonic plates, shaping the Earth's surface in dramatic ways.